Hi, I'm Michael Rick from Drake University, and I will be presenting uh, results of some research that I've been doing for the last couple of years. Title of this talk is Solid Geometry Problems Associated with the Perspective Three-Point Problem. Okay, please note my email address. I welcome questions, absolutely, either through email or any other way you can contact me. All right, a couple compelling problems in solid geometry appear to have been largely ignored in the mathematical literature to date. These problems are very easy to state, but mostly difficult to solve. However, recent advances in the analysis of the so-called perspective three-point problem make it comparatively easy to solve these problems. After stating these problems, each is split into two cases, an acute triangle case and an obtuse triangle case. This is done because the analyses of these problems wind up being quite different. For each case of each problem, a proposed solution is given. While no proofs are presented here, the claims that have been proved are identified as such. Extensive experimental evidence has been collected to support all of the claims using Mathematica and C++. Mathematica code for producing graphics is included. Oh, and so I want to say here, I'm working out of a Mathematica notebook, and when we get to the appropriate places, I will activate some Mathematica code to generate the graphics that I'm speaking of. And furthermore, I plan to make public this notebook, so it should be available to you. I'm going to provide a link at the end to a whole bunch of materials concerning the problems that I'm presenting, and that will include either include the Mathematica code itself or a link to that Mathematica code. So maybe 2 clicks to get to it. All right, let's state the problems. There are 2 problems, and here's the first one. So the first problem I call the 3 lines problem. Here's how it goes. We're going to fix directed lines L1, L2, and L3 in Cartesian 3 space, all passing through the origin and not coplanar. All right? Let alpha be the angle between L2 and L3. Let beta be the angle between L3 and L1. And let gamma be the angle between L1 and L2. Now, we're going to also fix 3 positive numbers, which I call angle A, angle B, and angle C, such that these sum up to pi. Okay? All right, now note that what I'm calling angle A is just a positive number, and it does not imply the existence of a point A. All right, that's potentially uncomfortable. Maybe you dislike it, but anyway, that's my notation. All right, we are going to pose a question now. This is the essence of the problem. To answer this question is what this problem is all about. All right, so here's the question. Do L1, L2, and L3 contain points A, B, and C, respectively, such that the triangle ABC has interior angles as follows? The angle at vertex A equals the prescribed angle A. The angle at vertex B equals the prescribed angle B, and the angle at vertex C equals the prescribed angle. And of course, I'm measuring angles in radians here. Having posed the question, what we seek is a logical combination of inequalities for answering this question, where these inequalities are as simple and intuitive as possible. All right? So I think it's clear, but by logical combination, I mean we're allowed to use and or, and not to connect these inequalities, to come up with a compound condition that when it's true, the answer to the question is yes, and when it's false, the answer to the question is no. Okay, that's our goal. All right, if you understood the 3 lines problem, here is the 3 rays problem. It's just a simple variation of the 3 lines problem, at least to state to analyze, it's significantly more complicated. All right, but anyway, the deal is pretty simple. It's a state. We simply replace the three directed lines with three rays from the origin. Okay, alpha, beta, and gamma pretty much like before, but now they're the angles between rays. And angle A, angle B, angle C, those are exactly like before. And the question is the same as before, except now we're trying to select points A, B, and C on the rays. All right, as I mentioned in the abstract, each of these problems naturally splits into two cases, which we could call subproblems. Okay, let's regard that we now have four problems. We'll think of them as distinct problems. So I have this somewhat cryptic, not terribly cryptic, because it's pretty clear in a second what these letters stand for. So I've got this this notation, this abbreviation LA. It stands for the three lines problem, but in the context where none of the angles A, B, C exceed pi over 2. And then I have LO, which refers to the three lines problem when one of these angles exceeds pi over 2. And the RA problem refers to the three rays problem when none of the angles A, B, C exceeds pi over 2. And the RO problem refers to the three rays problem when one of those angles exceeds pi over 2. So I hope that's clear. And I think it's clear that L stands for lines, R stands for rays, A stands for acute triangle, and O stands for obtuse triangle. Okay? And this next bullet is rather repetitious. We're looking for inequalities. I don't think I said this explicitly. We're looking for inequalities involving angle A, angle B, angle C, alpha, beta, and gamma, and then we're allowed to and or and not such inequalities together to come up with a compound condition that, again, if the answer is, if it's true, then the answer to the question is yes. If it's false, then the answer is no. That part I know I'm repeating. Okay, let's look at my proposed solutions now, beginning with the problem that is by far the easiest. All right, the LA problem is by far the easiest to solve. So we already know what the restrictions on A, B, and C are. Angle A, angle B, angle C. They have to be positive numbers and they have to sum to pi. But I now suggest that we have naturally these four conditions on alpha, beta, and gamma. Alpha plus beta plus gamma must be less than 2 pi. Alpha must be less than beta plus gamma. Beta must be less than alpha plus gamma. Gamma must be less than alpha plus beta. And I say either that's obvious to you, or if you think about it, based on the definition of these angles, remember that alpha is the angle between L2 and L3. And so forth. And if you think about it a little bit, claims such as alpha plus beta plus gamma is less than 2 pi are pretty evident, okay? You may have run into this in the context of spherical trigonometry, for example. I won't say anything else about that, but it's pretty straightforward reasoning. Okay, now, here's something that's not so obvious, something rather non-trivial. So far, to me, it's non-trivial. Okay, I claim that in the LA problem, there are no further restrictions, right? As long as the restrictions already mentioned are satisfied, then the question in the LA problem is answered in the affirmative. Right? It's basically an if and only if. All right? Okay, these conditions that are rather trivial that I've mentioned already, I'm going to refer to these as the evident or even trivial conditions going forward. And I'm going to always assume, going forward, I don't want to have to repeat myself and always be saying alpha plus beta plus gamma is less than 2 pi. So we're just going to tacitly assume that these evident conditions are always satisfied. Okay, the claim that no further restrictions are needed for the LA problem, to for me, is not obvious. It's not obvious. I tried to find an obvious solution, a trivial solution, if you like. I did not. I succeeded in finding a somewhat, slightly tricky proof. Okay? So I believe that I have proved it. In fact, everything concerning the LA problem, I assert, has been proved. That is not going to be the case with the other problems. Let's move on to the LO problem. Okay, besides the trivial constraints, the LO problem has extra constraints that are not obvious. I would say far from obvious. Okay, let's get a little evidence of the fact that extra conditions are required. So consider the situation where L1, L2, and L3 are pairwise orthogonal lines, right? Now, if you take a point A on L1 and a point B on L2 and a point C on L3, it's readily apparent, I think, that the triangle ABC cannot be obtuse, okay? It must be an acute or right triangle. So because it cannot be obtuse, we're going to get a condition here on the LO problem besides the ones we've already discussed. Okay. I'm going to argue that any solution to the LO problem must involve a quantity that I call D, all right? And it's quite a complicated polynomial. In its raw form, it's a very complicated polynomial in these quantities here. A little later, I'll explain where it comes from and the fact that it's actually been around for quite a long time in the context of the P3P problem, okay? There's another quantity that we're going to need called Q, and I'll define it later. Yeah, I have really just cooked that up in the last couple months, and it seems to work. There's an analysis underlying this quantity Q, and at some point I hope to present that in some form, but for now, just look at it as a quantity coming out of left field, you might say. All right, it'll be useful, very handy, in fact, to abbreviate cosine alpha as little c1, and little c2 will be cosine beta, and little c3 will be cosine gamma. And I'll use capital C1 for little c1 squared, etc. And I'll use capital C0 for little c1 times little c2 times little c3. Okay, so in the case of the LO problem where the angle A is greater than pi over 2, I'm now prepared to state my proposed solution. I claim that in this case, the answer to the question in the LO problem, let me read this. The question in the LO problem is answered in the negative if and only if the following compound condition holds. D greater than 0 and the following. Q is less than 0 or something else or something else. Okay? Then as you see, each of these something else's involve like angle A, angle B, angle C, as well as capital C2 and capital C3. All right? So there's a careful analysis and extensive testing supports this claim, but as yet it is unproven. And it's frankly really quite new too, only within the last few weeks. So I'm telling you this condition is my proposed solution when angle A is greater than pi over 2, and perhaps you can guess, what if angle B is greater than pi over 2 instead? Well, if angle B is greater than pi over 2, you simply permute the symbols, right? We can let angle A go to angle B, go to angle C, go back to angle A, and also alpha go to beta, go to gamma, go back to alpha, and that cyclic permutation will take care of the other possibilities, right? So, okay, let's move on. All right, now the RA problem, my investigation of it actually predates my investigation of the LO problem, and I've had this sort of figured out for, oh, basically a year, most of a year, I'd say. All right, so here's what I claim concerning the RA problem. The question in the RA problem is answered in the affirmative if and only if the following compound condition holds. All right, this is the ANDing of 6 pieces. The first piece says, if alpha is less than angle A, then C2 cosine angle C plus C3 cosine angle B is greater than 0. All right? And then that's ANDed with the second piece, which is similar, and ANDed with a third piece, which is similar, and that's ANDed with this piece, which says, if alpha is less than A, and beta is greater than angle B, and gamma is greater than angle C, then D is greater than 0, right? And then that's ANDed with something similar, and finally ANDed with one more thing that's similar, all right? And let me point out quickly that my arrow notation here is used for logical implication, and I say, of course. Well, if you've studied formal logic, then you recognize that P implies Q is equivalent to not P or Q, right? So I could rewrite this whole thing in terms of ands and ors and nots. All right. So what have I proven here? I have proven that this compound condition is necessary in order that the RA question have an affirmative answer. All right? It's necessary for that. But I have not proved it's sufficient. So if you're looking for something to do, maybe you can prove the sufficiency. It's pretty challenging, I think. All right. Then we get to the RO problem, but I'm going to punt on this one. Yeah, we're going to skirt around this one. Here's the deal. I have a proposed solution. It's actually in a document that I posted at this GitHub site. Okay. It's definitely the most challenging, and the only way I can find to solve it involves taking square roots, and I find that undesirable. Let me make sure it's clear. When I say, if I go back to the RA problem, here's my proposed solution. I am not saying that this is the only possible proposed solution, or that every proposed solution would be obviously equivalent to this, okay? That's not true at all. We're dealing with a bunch of inequalities, basically dividing this, geometrically corresponding to polyhedra, and then the union of polyhedra, and so on. And there are different ways. Well, I say polyhedra. It's not true. Look, this D greater than 0 is a nonlinear condition. But anyway, it's possible to imagine cooking up some other solution that looks quite different. I would claim that it would still have to involve capital D in a significant way, though. All right. Anyway, I'm still looking around for a more satisfactory solution to the RO problem. So we're going to skip that. What I haven't told you about yet is the quantities D and Q. I haven't really explained them, so let's do that. Let's get definitions. In fact, skip this first bullet, which just talks about a reference that I'm going to get to when I get to references at the end. So here, this bullet says the quantity D is discussed. It's something that I refer to as the discriminant of Grunert's system. Okay? And let me explain that briefly. So this P3P problem is a very old problem. Well, very old is relative, but it's a problem that was posed and solved in the 19th century, in the early to mid 1800s, by a mathematician named Grunert, and his solution involves a system of 3 quadratic equations, okay, but those can be reduced to a single equation involving a single variable, a fourth degree polynomial in a single variable, the discriminant of that fourth degree polynomial can be factored, and the really significant factor in it is what I call capital D. All right? So the point there being, capital D is really quite old. Nothing new about capital D. However, a few years ago, I came up with a way of computing capital D that's efficient. Okay, because as I said, in its raw form, capital D is a really complicated, messy polynomial. All right, here it's not terribly important to understand. Frankly, it's not important to understand anything on this slide. That's something you never tell students. All right, but here's the story. If you follow this, great. If you don't, it doesn't matter, right? But I'm going to give you a working definition for capital D and also for little q. All right, so in order to get D, what I do is I start with a triangle A prime, B prime, C prime that is similar to triangle ABC. So it has the same interior angles, okay? But this new triangle has its vertices on the unit circle in the Cartesian plane, okay? And moreover, there are angles, phi1, phi2, phi3, that sum to 0 and are such that the coordinates of A prime, B prime, and C prime are respectively x1, y1 equal to cosine phi1, sine phi1, comma, x2, y2 equal to cosine phi2, sine phi2, comma, x3, y3 equal to cosine phi3, sine phi3. All right? Is there any reason that you should believe that this is always possible? Well, you certainly believe that you can take a triangle and scale it and translate it to get it onto the unit circle, right? And then all you have to do to fulfill this angle requirement is rotate that triangle. And if you rotate it in the right way, you can satisfy this triangle requirement. So work that out for yourself if you want, or trust me. Okay. Then we have these, on our road to defining capital D, we're going to define some other quantities. The first of which has a very geometric meaning, and I'm going to get to that in an upcoming slide. But for now, capital H is defined to be 1 plus 2 times capital C0 minus capital C1 minus capital C2 minus capital C3. Yeah? Now some good news is we're going to skip the definition of those three guys, L, R, and K. I don't really need K. But let's skip the definitions of that. And then we finally arrive at D. And if you notice, D is a homogeneous fourth degree polynomial in capital H, capital K, and capital L. Okay? And it actually has a pretty interesting geometric significance. If you set that equal to 0 and treat that as a homogeneous polynomial in 3 indeterminates or 3 variables H, K, and L, what you get is a homogeneous equation for a curve known as a deltoid curve. So it's a pretty standard fourth degree curve. Okay, so enough of that. Now we'll say even less about Q. So just start with these quantities J2, K2, M2, J3, K3, M3, and then define Q to be something squared plus something squared minus something squared, right? Yeah, there's a geometric meaning to this thing too, but we're not going there, okay? And it plays very much of an auxiliary role, whereas I think D has an absolutely critical role in what's going on here. Okay, we've arrived at what I consider to be the fun part of this talk. Certainly hope it works out that way. Oops, it won't work out that way if I keep getting sloppy with these buttons, with these keys. All right, so I'm going to demonstrate by means of some Mathematica graphics. We're going to plot some graphs. But before I do, I have to point out that capital H can also be written this way. as 4 multiplied by a certain sign times another sign times another sign times another sign. And the real significance of that is this. So remember the 4 inequalities for alpha, beta, and gamma, the ones I called evident, such as alpha plus beta plus gamma is less than 2 pi. Okay, those 4 requirements can be expressed more succinctly by simply saying that capital H is greater than 0. Okay, that's one more thing for you to work out on your own. It's kind of interesting. So anyway, we are going to assume capital H is greater than 0 going forward, right? Always. All right, so I'm going to first present a demonstration for the 3 lines problem. Yeah, and in using the code, the user has to specify the triangle ABC. So you've got to fix a triangle ABC, but you've got to really specify the interior angles ABC. And that's what I should have explicitly had the user do, but for some reason, when I wrote this maybe a year ago, I instead had the user specify 2 side lengths, B and C, and the interior angle between them, angle A. Okay? So that will specify the triangle. But it's really important to realize that the scale of the triangle is irrelevant, right? If you can fit in a certain triangle between the lines, if you can fit a triangle in there, then if you scale that triangle, you can still fit it in between the lines. So the scaling of the triangle, irrelevant. It's only the shape of the triangle, you know, and of course that depends on angle A, angle B, and angle C, the interior angles. Yeah. All right, the user also has to specify a value for C3, or what's equivalent to that, specify a value for gamma, right? Remember that C3 just means cosine of gamma. All right, with those parameters fixed, the program is going to, first of all, seek out pairs C1 comma C2 that are feasible for the lines problem. And so what do I mean? So remember, C1 is cosine alpha and C2 is cosine beta. So we're really seeking out suitable values for alpha and beta, okay, that produce an affirmative answer to the lines problem, okay? So together with the parameters that were fixed, namely the interior angles and also the angle gamma, we're basically looking for the alpha and beta that will lead to an affirmative answer to the lines problem, right? Okay, now it's more convenient and frankly more aesthetically pleasing to work with the cosines. So instead of thinking of pairs alpha comma beta, I'll think of pairs C1 comma C2. And I'll treat such a pair as a point in a plane. Yeah, and I'll call the plane the C1, C2 plane to emphasize that the horizontal axis is for C1 and the vertical axis is for C2. Okay, all right, so now think about all of the feasible points or pairs, C1 comma C2. Okay, if we plot that, we get a certain region of the plane. And in the graphic, that will be the blue region, right? All right. Okay, how are these points generated, by the way? Okay, this is something that I really like. I was using one method way back when I had C++, when I was doing stuff earlier in C++. But lately, I've been leaning on a paper by a mathematician named John Wetzel, in which he describes a method by another mathematician named John Sullivan. Okay, I've extended that so that basically can parametrically generate all of the possible capital A, capital B, capital C triples that basically all the affirmative all, yeah, all the solutions to the lines problem, if you like, okay? All the ways that you can put a triangle into three given lines. The lines are fixed, L1, L2, and L3. They're fixed, I should say that. L1 and L2 and L3 in this method, we've got those lines fixed. And we're trying to fit a particular triangle in the sense of the lines problem in there, okay? So this method will do it. Now, of course, I can't generate all of the possibilities. There's infinitely many. Even with L1, L2, and L3 fixed, and my triangle fixed. Now, I'm now thinking, of taking a triangle like cardboard, something that I can physically move, a triangle ABC that I can pick up and move and try to lay into those lines so that the vertices fall on the lines. Yeah? Well, okay, well, now I said that we're fixing the lines L1, L2, and L3. I misspoke because we're actually going to allow line 3 to move. We're going to allow line 3 to move. And what that's going to do is allow the angles alpha and beta to vary. Huh? So if we're allowing alpha and beta to vary, that means we're allowing C1, C2 to vary. Okay? Anyway, we wind up with allowing those to vary, we wind up with infinitely many points, infinitely many ways to go. But this method, when implemented in code, is going to only generate finitely many, but it's going to generate a lot. So I forget how many. Let's say hundreds of thousands. Okay. Anyway, we wind up looking at a region blue that corresponds to the possible feasible C1, C2s. Now, another region, which is going to be represented in yellow, is going to be produced using my proposed solution to the lines problem. Okay, so what we're going to do in the yellow region is we're going to include points C1, C2 that I allege are not feasible, right? And the reason I decided to go with not feasible is because I don't want this region to just overlap on top of the blue region. Instead, this region of points that I allege are not feasible produces this yellow region, which I will show you partitions or does not overlap the blue region, and together they partition the interior of a certain ellipse. Let's talk about that ellipse. Remember that we're requiring that we're only interested in when capital H is greater than 0, and that corresponds to the interior of an ellipse. All right, all of our focus is inside the interior of that ellipse. We don't care anything about what happens outside that ellipse. So what I'm now claiming is that the blue region and the yellow region are going to partition that ellipse. Okay? And I would say, I might be wrong because maybe a less than should be a less than or equal to, or something like that. That would amount to being wrong by a set of measures 0. We wouldn't be able to see it. Okay? So I'm not gonna say that I've gone through that thoroughly. Some fine-tuning where a less than maybe has to be turned into a less than or equal to, that's possible. All right? One last thing that we're going to see in the images, the graphics, is a red curve. And that red curve is where D is equal to 0. Okay? And as you'll see, part of that red curve serves as a boundary between the blue region and the yellow region. Okay? I got a whole lot more figures. We're going to see a couple of these images, but there's a whole bunch more in this document that I call 4 problems, which is available at the website the GitHub site that I alluded to, and we'll see again in the references. Okay, it's time to play with code. Yes, this is Mathematica code. You may know nothing about Mathematica. That's fine. We're not going to talk about this code, really. We're not going to investigate the details, okay? Or maybe just this. I'll say that I'm about to define a function called disk, but that's really my capital D. And also a function called little q, and that is my little q. Okay, so I've activated that cell, which defines those functions. Now I'm going to go down and activate this cell, which does everything I just described, generates those two regions in that curve. All right, and there it is. You might have trouble seeing the red curve right now, but don't worry about that. Kind of like saving that for a moment. So, of course, you see this blue region, and the graphic just settled down. The fact that it has a couple different shades of blue, it doesn't matter to us, but it does have to do with the fact that there's sometimes multiple ways to fit a triangle. So the blue region, as described, is produced by an extension of John Sullivan's method. And the yellow region is what I said it was. It represents the points that my proposed solution say are not feasible points. They should not be possible to generate. Okay? And apparently I got it right. Okay? The points that I'm saying should not be possible for Sullivan's method to generate are indeed the points that Sullivan's method can't generate, up to maybe a set of measure 0. All right, let me turn off the blue region. If I turn off the blue region, we're going to see the red curve more clearly. There it is. And again, the red curve is where capital D is equal to 0. All right, there are portions of that curve that are irrelevant as far as separating the yellow from the blue. But obviously, there are quite a big chunk of this red curve does serve as a boundary between the yellow and the blue. Okay? And by the way, we're looking at, this is for an obtuse triangle. Happens to be that the angle C is obtuse. I know it's probably impossible to read this label here, but it's telling me that in this case, the angle C is greater than pi over 2. All right? So this would be an example of the LO problem. All right. Now, if I increase B, like about this much, I certainly hope I get it right. Okay. I increase B, and I should be getting an acute case here. Has this thing failed me? It certainly didn't fail me in rehearsals. I'm not seeing any blue region this time. Let's try that one. Oh, am I being daft or what? Look, I turned off the blue region feature, that's all. So let me turn on the blue region feature again. So again, we're looking at acute triangle case. And yeah, and as I expected, the entirety of inside that ellipse is now blue. That's telling us that all of the possibilities in there are feasible as expected, because that's what the LA problem basically says. The LA problem basically says all that's required is that capital H be greater than 0, and that means anything goes inside this ellipse. All right, that's the end of that. Let's move on. All right, so we now come to the 3 rays problem. I'll try to go quickly through this. The story is similar. The constraints are more complicated. The code that I wrote only works for 2 cases. When ABC, triangle ABC, is an acute triangle, it works. Also, when angle C is greater than pi over 2, it works. It does not work when angle A is greater than pi over 2, nor when angle B is pi over 2. Chalk that up to laziness if you like. All right, so here we go. I'm going to activate that. And what we're looking at here is an example for an acute triangle. Okay, it hasn't settled down yet. Give it a moment. Now it has. All right, and notice that the blue region sort of comes into 3 pieces here, top right, bottom left, and then this little sliver, okay, this little bit here in the top left is also included in the admissible pairs, C1 comma C2. All right. And then my proposed solution says that the yellow region represents where my proposed solution says those are not feasible. And again, it looks like I did that correctly. It seems to partition the interior of the ellipse. And also, most of the red curve this time doesn't play any role in the separation, but this little portion of it clearly separates the yellow from the blue. Okay? All right, now this label that, again, you can't read, I guess, says acute. So this is an example of an acute triangle. I could get an obtuse triangle by using these sliders again, but I choose not to. I'm going to go instead to, come on. I'm sorry, let's see. Okay, here I am towards the bottom of the code. What I'm going to do is take certain parameter values that I had canned in here and comment them out. And then I'm going to take other canned values that I had commented out and uncomment those out. So I'll try it again with different parameter values. All right, and we get this, right? That's not settled down yet. Okay. Panopto tells me my audio is not working, but I don't believe it. All right, now it's settled down, and it's the same story pretty much. Figure looks different, but there's a blue region and a yellow region. Together they partition the interior of this ellipse, and it's very clear that a portion of the red curve serves as a boundary between those two. All right, there we go. Now let's get rid of that graphic, and let's move on. All right, so last thing I want to demonstrate is this, because I'm very fond of these images, to be honest with you. So now I'm going to ask, in three-dimensional space, let's call it C1, C2, C3 space, where one axis is labeled C1, one axis is labeled C2, and one axis is labeled C3. Let's find out what the surface corresponding to, the surface D equals 0 looks like. Yeah? We're going to continue to restrict our attention to where H is greater than 0. And I don't want to spend too much time on this. Let's just do it. I'll explain about, maybe I better explain about this. All right. First, we're going to look at a case where triangle ABC is obtuse. And in that case, we're going to see a surface that is self-intersecting. And it separates the region where H is greater than 0 into 3 subregions. Okay? On 2 of them, D will be greater than 0. On 1 of them, D will be less than 0. Okay? And here's the thing. Only on 1 of these 2 regions where D is greater than 0 do we have points that are not feasible, right? That do not solve the lines problem. Okay. If instead we use an acute triangle ABC, well, this time we're going to wind up with only 2 regions. It won't be self-intersecting. The surface will not be self-intersecting. It'll separate space into, or the interior of that H greater than 0 will be separated into 2 regions, one where D is less than 0, one where D is greater than 0. And moreover, the surface D equals 0 will be homeomorphic to a sphere. All right? But again, when the triangle ABC is obtuse, we have a self-intersecting surface, and I would argue that that is essentially the reason why the LO problem is has a non-trivial solution, yeah, as opposed to the LA problem, which has a trivial solution. Okay, let's just fire this up. I want to get through this pretty quickly now. All right, here it is in the case of obtuse triangle. So as I said, in the obtuse triangle case, we have a surface that is self-intersecting. Um, the curve where the intersection occurs on this white curve here. This white curve is where this surface intersects itself. Now, perhaps I should have started by explaining why I decided to make this tutti frutti. Why did I make this multicolored? Well, for one thing, this surface has a symmetry. If you negate any two of C1, C2, and C3, the surface is invariant. Okay, it's invariant under the negation of any two of C1, C2, C3. Okay, if you like fancy talk, it's invariant under the action of a Klein-4 group here. All right, now if I change, let me see, I think I better up phi2, increase phi2, and I'm hoping to get it, yeah, I did. Okay, so this one is for acute triangle, acute triangle ABC, and I don't know if you can tell, but there is no longer self-intersection, and as jaggedy as this looks, it's actually homeomorphic to a sphere, right? Okay, let's get rid of it. Boom. All right, some afterthoughts. So at some point I noticed that my solutions to the LO problem and the RA problem, they can be expressed entirely in terms of C1 and C2 and C3, avoiding any explicit mention of alpha, beta, and gamma. And that in doing so, what I have is a system of polynomial inequalities in C1, C2, and C3. And I have got this idea that some results in algebraic geometry, it should be possible to apply them, I think, to prove that my proposed solutions are indeed correct. Okay, so I don't know that for sure, but when I think about things like the Wu-Rit decomposition, seems to me something like that should work. Okay, let's move on very fast. A few years ago, I presented some slides at a regional meeting of MAA here in Iowa, and I produced the results that I had in a paper which never got published. But I think one of the ideas, I worked with a student here at Drake, and I came up with this idea that I really like, that basically says that the P3P problem, which is a problem in three-dimensional space, can be reinterpreted as a problem on the surface of a sphere. Basically, you take the directions that are involved in the P3P problem, and you reinterpret them, and you wind up looking at a reformulation of P3P that involves four great circles on a sphere. Okay? Well, the same thinking applies to the problems discussed here. And I'll close by saying that I've come up with a little puzzle. Okay, I like to think of it as a puzzle, but it's a mathematical fact. Okay, because I've proven my claims about LA problem. And so now I claim the following that concerning this puzzle. So first of all, here's the puzzle. The puzzle starts with a sphere, and you draw three great circles on the sphere. You also have a movable ring the same size as the circles, and it has markings on it. Okay, now there's some restrictions on the markings. Basically, let's not go there. It's not a big restriction. The goal of the puzzle is to place the ring on the sphere so that the ring becomes a great circle and the markings line up with the circles. So the markings fall on the other circles. Okay? I will not get into detail here. So I think that I will go to my references, try to go quickly here. If you're interested in learning more about the P3 problem, I would recommend this paper in 1997 that pretty much anybody who writes anything about P3P includes this paper as a reference. So this is a very standard reference. It was not written as so much as an introduction, but mainly as a comparison of different methods for solving P3P. But it certainly does include an introduction to the P3 problem. So I definitely recommend Halleck et al. Now, the paper where I introduced my efficient way to compute D is this one, on the discriminative Grunert system, blah, blah, blah. More recently, I wrote this paper with Bo Wang, a Chinese researcher, who I've unfortunately fallen out of touch with. But anyway, this is our paper, and it too talks quite a bit about the discriminant of Grunert system, my capital D. Yeah? And finally, the paper of Wetzel that I said it explains John Sullivan's method is called An Ancient Elliptic Locus. It's in the American Mathematical Monthly from 2010. And finally, I want to go to my GitHub site and point out that we've got this paper here that I mentioned before. Well, okay, time out. Is this thing? Oh yeah, that's what it's displaying. This is the paper I was talking about. So this pretty much just covers the same material that we've been looking at in a little bit more detail. It includes the RO problem. Okay, and it has a whole bunch more of these figures. Okay, but now you understand what those figures mean. So these figures are for the RA problem, and then there are figures for the LO problem, and then there are figures for the RO problem. All right, I also have these three-dimensional figures that I showed you. So that's that surface in the case of an acute triangle ABC. This is that surface in the case of an obtuse triangle ABC. Okay, so now I appreciate your staying with me. Obviously, if I'm talking to you still, you stayed with me for the whole talk, and I appreciate that. Thank you. Right, thank you for your attention, and by all means, if you have any questions, contact me. Okay?